In typical fashion, there's a bug. What's going on, vlog? You guys had a great day. It's already 8:34 p.m. So this is a very, very late start for me. I was quite busy all day, so couldn't really get much done. So I'll keep this short, but in the interest of moving on to recurrent neural networks tomorrow, I kind of want to just take a last stab at optimizing my DQN. It doesn't have to be perfect for tic-tac-toe because eventually the plan is to grow it for 3D tic-tac-toe. Um, may not be anytime soon. I may take a break from this project and work on something else in the meantime. But yeah, I mean, tic-tac-toe essentially, search is always either going to win or draw. So search is probably the best algorithm for tic-tac-toe because there aren't really too many states for it. But what I'm more interested in is for 3D tic-tac-toe. So if DQN can't play a perfect game for tic-tac-toe, I'm not really too worried, but I kind of do want to be able to tweak and figure out what makes it perform, what makes it train better. And so that's what I'm going to spend time on today. Now, yesterday what I mentioned was I wanted to switch up the training a little bit for DQN, and I wanted to create a random player that just plays randomly and use that random player along with DQN itself and along with Naive to train the DQN network. I don't necessarily think I need to do that. I think all I just need to do is just tweak the epsilon value, which is just the probability that DQ1 will make a random move. I think in my original data set or my original training, I just set it to 10%, which is okay, I think, but maybe upping it to maybe like 20% might be that little tweak that helps it see random moves a lot more. So yeah, I mean that's the plan. I will do that. I'll probably spend maybe about an hour on it. I think it's good. I think all it is just that it just needs to be tweaked and just have better training. But I'm encouraged with what I'm seeing so far, and that's that. So I'll keep this short. That's the update for today. Not really too much going on. So I'm just doing some quick research, and I found someone else who's also implemented DQN for tic-tac-toe. Although he did use Python, and he used some libraries in Python, whereas I'm doing it from scratch, so it's a little different. But I'm still just trying to learn from what he's done. So what he's done is kind of similar, but kind of different. So he's given the agent a reward of -1 if it loses, but also he's also trained the agent to avoid illegal moves by giving it a reward of -10 if it makes an illegal move. And so an illegal move in tic-tac-toe is essentially just if there's already a player there and the DQN tries to go in that position. So X is in the top left corner and the DQN goes, oh, I'm going to go in the top left corner. That's an illegal move. And so you try to incentivize that behavior without explicitly telling it what are legal and what are illegal moves. That is something that I never really got to in mind. It was in the back of my mind, but I just said, you know what? I'll just feed it legal moves. Just make it easier. But another thing that's really interesting to me here is that this person's saying that perhaps, and now I'm curious, perhaps if you did something else, which was to incentivize the AI to avoid losing moves, perhaps that would provide, or perhaps that would produce different results than giving it a reward of -1. So essentially, rather than giving it a reward of -1 if it loses, you give it a reward of 0.1 or 0.2 or whatever if the move that it made kept the game going. And so they sound like the same thing, but with neural networks, you never really know, and you just have to try. So if there aren't really if I don't really have to make too many tweaks, or if there's not really anything major that I have to fix tonight, I might just do that. I might just experiment and run two different neural networks. One I'm not going to do the illegal move thing though. But one neural network where I give it a reward of -1 if it loses, and then another one I give it a reward of 0.1 if the move it makes keeps the game alive, and then we'll put them together tomorrow, and that'll be that for DQN. But still doing some research, and we'll see if there's anything I can find about how to create the ultimate tic-tac-toe playing DQN. So this is what I was looking for. So this person, he used an epsilon of 0.2, which is kind of what I was saying as well. Might be better, it might work better because it allows the DQN to experiment a little bit more and gives it, rather than a 10% chance of making random moves like I have it, a 20% chance of making random moves, and so it'll learn more and more. This person also used Atom, which is a different optimizer that I'm using. Maybe that, because there are multiple variables that are different from mine. Maybe that also plays a factor in his being more successful, but we'll see. We'll see. I'll experiment with epsilon of 20% or 0.2, and we'll see what that does. Okay, so here's another article. Now, what's interesting to me with this article is that I'm not sure, maybe I implemented it wrong, or maybe, yeah, I think maybe I might have implemented something wrong. But basically, what he's saying is that, so you perform backprop on the policy network, which is exactly what I do. Then he says we obtain the maximum Q value for the next state from the target network. I do mine from the policy network, so I don't know if I'm doing that wrong, but it seems to work, so I'm gonna leave it as is. Now, something that is interesting is that I can't remember how many games I had DQ1 play through, but he's saying that for him it took 2 million games to train it to be able to play effectively and draw with Minimax over, and so this table here shows the results of DQN versus different types of algorithms over 1,000 games. So I mean, for me, I'm just looking at, maybe I just need to train it more. I don't think he's stated his hyperparameters, but I'll keep looking for that. This is really interesting. So what he's done is that he's also offers the same reward for a win as for a draw. Wonder why. And his argument is, playing as X, the network can end up losing to Minimax. And so when he makes the reward for a win or draw the same, that seems to resolve the problem. I'm not sure I follow that. I'm gonna take like most of what's on here with a grain of salt. The most useful parts for me though are the 2 million training games, and I'm just curious. So if I have time, I will just try his thing where he offers the same reward for a win as for a draw. Ooh, here's an interesting idea from Stack Overflow or Stack Exchange. I'm just taking inspiration from this first first point here. But essentially, I think a really interesting idea would be to, when I'm training both networks, have one agent be the one that learns, and then the other agent be the one that always tries to play optimally. And so as it learns an optimal tactic, it'll also learn how to beat that optimal tactic, and that will make it a much more well-rounded AI. Okay, so here's what I've mainly learned from most of my research. What I've mainly learned is it's highly subjective. The way I'm encoding my data is very different from the way everyone else is encoding theirs. A lot of people just use straight up binary coding, so 1 for X, -1 for O, and then 0 for blank, which I have that implemented as well. There's another research article that I read though that said binary coding was not the best, especially for tic-tac-toe, or especially because there are 3 categories in tic-tac-toe. So yeah, I have to look up that article and remember why. So yeah, I guess the only thing I can really do is just experiment, just out of curiosity, and just for tomorrow morning, I will turn on and I'll just do a couple of experiments. I think one thing I'll do is, I kind of forgot all the other stuff I researched because I'm tired. I forgot everything that I took a look at in like the last half an hour or so. But one thing that stuck with me is training the neural network such that, one player is playing doing all the learning and playing randomly. There's something in my hair. Yeah, what the heck is that? Whatever. One player is playing randomly, and then the other player is always trying to play optimally. And I think that will be a good way to train it. What else was there? Oh yeah, so training it for 2 million games. That was another one. Changing the reward function. Nah, nah. I give up on that idea. Nah. I give up on that. Yeah, I mean, generally speaking, I don't really think there's anything major that screams that there's anything wrong with what I've done. I think it works fairly well. I just have to spend a little bit more time tweaking it and getting it to perform exactly like I want to. So that's tweaking the number of layers, number of nodes in each layer, tweaking and experimenting with different encoding types, tweaking and experimenting with activation functions, dropout. So yeah, there's a lot more tweaking involved than I would like. And again, you know, this is just, we're just prototyping, or we're just experimenting with how it will work, so that when we go with 3D, I'm fairly confident that it works. So I don't necessarily need to, you know, get it perfect, but for my own curiosity's sake, I will just run 2 different experiments, and then that will be it for tonight. And oh crap, it's only 9:40 and I have to edit this video. Okay. So I will be calling it a night. I have 2 different AI, or 2 different experiments going on right now. This one is, well, what is this one? Oh, this one is just with epsilon 20. So epsilon 0.2, and that's what's going on here. So hopefully it'll be making more random moves while it's training, and it'll learn better. Right now we are about 4,500 training instances in, or epochs in. So I'll let that train overnight, hopefully get to about 2 million or so by the time tomorrow morning hits. And up here, what we have going on up here is that the experiment where player 1 plays with an epsilon of 0.2. So player 1 is kind of the one spearheading the learning and playing and injecting some random moves in, whereas player 2 always plays optimally. So whatever player 1 has learnt, player 2 will then try to implement and play that. And so what it forces the network to do is it forces it to learn an optimal move, but then also learn ways around, or ways to beat that optimal move. And so that is the plan. And that's that. This is a faster computer, so this one's already at 8,000 epochs, and hopefully this one will hit 2 million before tomorrow morning. This one, I don't know. This one's still at 5,000, and I started it before that one. But that's just a small little technical detail. It's not really too important. So that's that. I'll let that go on. It's about 9:50. I hope I can quickly edit this vlog, get it out, and then get some sleep. And I'll see you guys bright and early tomorrow. In typical fashion, there's a bug. It seems as if oh my god, it seems as if the save function that I implemented, and yeah, this one just bugged out too. It seems as though I have to restart both training instances. Oh my god. But it seems as if the save function that I implemented just isn't working I don't think I actually implemented it for the first version of DeepQ. I think I went ahead and I implemented it for the second version, so I just gotta fix that and get back to training. Okay, we're back at it. Everything's back up and running, and we're back to training, and we'll see what happens tomorrow night. And good night finally this time, hopefully, if nothing else goes wrong.